Okay, welcome everyone again. We're waiting until we had more people join this morning. Welcome to the second day of the Explainable Agency in AI workshop at AAAI 2021. I'm Rosina Weber from Drexel University, and we will start our program today with an invited talk from Margaret Burnett. She's a distinguished professor, ACM distinguished scientist, and a member of ACM Chi Academy. And she's a professor at the Oregon State University. Margaret has co-created the explanatory debugging approach, and she has 2 decades of experience evaluating system usability and usefulness with human participants. On a DARPA XAI project, she is now working with Oregon State University team to design an explanation ontology from a user perspective. The combination of information foraging theory with decision theory, the explanation UI support for human problem solvers, and will lead empirical investigations with human participants. I would like to echo the request from Margaret. I also encourage everyone to have your cameras on. I'm sure everyone will feel much more comfortable sharing and asking questions and participating. Remember, this is a workshop and we are all here to learn from one another. Margaret, thank you very much for joining us today. And go ahead.
Okay. Oh, thank you very much, Rosina. Oh, and please do give me heads ups as I start to run out of time. That would be awesome. I just love these kinds of interdisciplinary conversations and groups. A grad student friend of mine back when I was a grad student once told me that the big bangs really happen when you bring 2 completely different backgrounds and theories together and start talking about what could happen. And I'm a firm believer in that. So today we'll talk about something maybe a little bit different. I'm going to put forward the proposition here that explaining AI well includes explaining AI fairly. So let's talk about that. Oops, and it won't let me go forward. Okay. So AI in society, people who are working in the AI space, we all have a lot to think about. We've got automation displaced angry people, social media of interest to you bubbles, kind of an overly pervasive attitude that the impact of what AI causes isn't my job. And all of this adds up to what I call social debt, which is kind of analogous to technical debt, things that we've been doing over the years that are coming back to haunt us. But there's some good news, and that is that paying off that debt is within our power because tech is power. And in fact, tech is the power. And so there are some things that only we can fix. And one of them is, of course, being transparent about AI reasoning. We are the only ones that can do that. But we should be doing it in a more inclusive, fair way. So let's just be frank about who we're explaining to today. Mostly, we're explaining to people like us. We're explaining to machine learning people, or maybe if we're really stepping outside the box, to software developers. But even if we purport to be explaining all the way to end users, we tend to be envisioning educated people in high-paying jobs, young-ish, in developed countries, men, or, quote, just like men. And why is this happening? Well, here's some demographics from the US, which is where I'm from. Look at who's building these systems. We tend to build for people whose heads operate the way we think their heads operate. In other words, the way our heads operate. So the orange are members of underrepresented groups in our society. And as you can see, most of the people who are producing AI and explainable AI are men. They all have college degrees. They're almost all not members of underrepresented groups, Asian and white mostly, and they're all at least middle socioeconomic or higher. So let's just put that picture over in a little corner and look at who we should be explaining to. So these are the demographics of US society. And these are the consumers of AI because these are the people being affected by AI. Of course, not surprisingly, only about half of those people are men, a little less than half have college degrees, and so on and so forth. So look at this mismatch. No wonder we've got this situation. Sorry, you've got my morning voice here. It's early here in Oregon. I'll lubricate myself with coffee. That'll cause me to go faster and faster. Which brings us to unconscious bias in explaining AI. So does XAI support a variety of users? No, it mostly supports people like this, unconscious bias. Not people like these people, and most certainly not people like these people. Okay, we should be explaining to all of these people. So, sorry, I need to move my Zoom controls over. They're hiding things. Here are some motivating examples about why we need to explain fairly, and to have it particularly motivating, I'll mix fairness in. So we're going to explain fairness fairly. Zoom kicking in again. Okay, so here's one motivating example. A small business owner wants a loan. Let's say they're financially struggling, race Latinx, and the system says no. And what they are asking is, why not? Why didn't it issue my loan? And even more, how can I fix this? Coming back to some of the actionability talks we saw yesterday. Here's another one, a single parent, they want a job, so they're job hunting. Woman, education, no college, SES, socioeconomic status, low. And they're saying, why didn't it rank me higher for jobs like that? I'm qualified for them. They have a right to know. Somebody driving, they bring up Google Maps or whatever, and it suggests a route. This is a Black woman, and what she'd like to know is this Google Maps route safe for me? If I go through that neighborhood, are people going to call the police because I'm Black? Okay, these things happen, and she has a right to know, but we're not explaining any of these things to any of these people. So the goals that I think are really important for us to think about is that we want diversity of thought. We want this in our society, we want it in our businesses, and so what we want to do is support that in our systems, because if we don't, we'll stamp it out. And this is critical. We also want appropriate trust. We don't want people to trust AI more than is appropriate. If the system is lame, we don't want them trusting it. And we want people to be able to make informed decisions. What we don't want is to fix the people and force them to all be the way our wonderful explanations wishes they were, okay? Wish they were. Anyway, and we certainly don't want to convince them to trust AI. We want appropriate trust, not blind trust. So what we need to do to achieve goals like this are fix the explanations, support ways for diverse humans to calibrate information, make decisions, and trust at an appropriate level. So in fact, what I've just said, maybe some of you are thinking, boy, that's hard. And you're right, it is. But it's even harder. because besides diversity of thought, something else that we often don't think about is there's diversity of situation. And so some people, including me, work on trying to understand which explanation is better. But there is no better situation unilaterally, because different explanation strengths depend on the situation that's being explained. So here's a graph from one of our papers. And all I really want you to notice is, wow, this is all over the map. Diversity. So as it happens, the x-axis is saying different situations. So we have situations 1 through 14, and people are trying to predict what the AI is going to say about it, and they have different explanation styles. Each color is a different style. So look at this. In situation 4, the yellow explanation is the most effective at helping people understand it and predict it. Not very good, but better than the others. In this one, the blue explanation is better. In this one, the green explanation is better. And in this one, this kind of tan color explanation is better. Okay, they're all over the map. And you'll also notice that over time, it isn't as though any one of these is improving either. Okay, diversity of situation on top of diversity of thought. It's hard. And so some of you may be thinking, wait, this is hard. This is too hard. And us, we're not social scientists, but lucky for us, there are all these people with massive social science backgrounds who are coming to our rescue. And we've been hearing from some of them at this workshop, for example, Tim and Shane Mueller, both. So we have people bringing us things on a silver platter, helping us to understand how social science can come together with the explanations that we're designing. And so here's another one saying, yeah, but all these people, all these situations, we can't do everything at once. And you're totally right. So I'm going to let you off the hook. Let's just start with gender. We'll just go that far, okay? All right. So hopefully by now you all are inspired and saying, yeah, I want to do something. How? But before we go forward with how to, let's talk about how not to support diverse genders with explainable AI. Shrink it and pink it. Please do not be doing this. This is a real thing. If you Google search, you'll find it. It's unfortunately a bit pervasive. I'll tell you one story that dates back a ways, Dell's pink laptops. This really happened in 2009. Some brainy person at Dell said, oh, wow, you know, we need to sell to more women. I have an awesome idea. We'll paint our laptops pink. And we're going to do a website too to go with it. It's going to be awesome. It's going to have recipes and stuff. Guess how long that website lasted? Just guess. Anybody, just speak right up.
2 minutes. That would be too much.
That would be too much. Actually, this is before the days of Twitter, 2009. That website lasted 20 minutes before they took it down. Before they were so embarrassed, they took it down. And this is before Twitter. Okay, but unfortunately, that wasn't enough to teach everyone. So here's another one. This dates back a while too, but unfortunately, this one is still on the market. Pick for her. So some brainy person at BIC also decided we need to sell to more women. I have an awesome idea. We're going to have some pink and purple pens and a label for her, and we're going to raise the price. And they did. And by the way, the price is still higher for these pens, whose only difference is the label and the pink and purple. Okay. Yeah. So these things are wrong on so many levels. But one of the many, many reasons these are wrong is that they don't work. Because within gender, we're more different than we are alike. So the solution can't be assuming that there's somebody out there that's typical. The world doesn't divide into typical men or women or other genders. And so what it can't be is about dividing the world up. What we have to do instead is think about this as a debugging problem, taking down the things in our explanations that are making it, that are just not great fits for certain ways of problem solving, taking those things down as though they're bugs so that diverse ways of problem solving can succeed at making good sense of what our explanations are trying to let them do. So I can't emphasize enough, it's about debugging, not dividing. All right, so how do we find these bugs in our XAI systems? So my lab has been working on a way to sort of apply social sciences, well, not sort of, to definitely apply social sciences to exactly this problem. And so we've been working on a method that's called GenderMag, which stands for Gender Inclusiveness Magnifier. GenderMag is a method, a process that you use to evaluate the inclusiveness of the explanations or other kinds of software you're building. And it works when what you're trying to do is support a user problem solving, which is exactly the case with Explainable AI. They're trying to figure out what's going on. GenderMag has some personas, and the persona's job is to bring to life 5 cognitive facets, 5 ways of problem solving. And this is embedded in a step-by-step process like this. So you start by picking one of the personas that's included in the method. I pick Abby. You can see that here I've kind of dressed Abby in black because in this scenario, Abby is going to be a judge. But Abby can be any job title you need. You pick a use case or a scenario in your tool that you're going to evaluate. So here, the tool that we're going to evaluate is something I'll call the judge's assistant, and it predicts recidivism, which is how often a defendant is likely to be a repeat offender. And so what Abby, the scenario here that Abby is in is she's, the defendant has been convicted. She's trying to decide how much to sentence them for, whether to send them to jail, parole, community service, 10 years, 1 year. So that's what she's trying to do with the help of this assistant. So the way GenderMag works is you walk through the scenario, that's this one, using a set of sub-goals and actions that we, the tool builders, wish the user had. And so the first sub-goal that we wish Abby had right now is understand the prediction, okay? With, of course, XAI to help her. All right, we're going to put this on pause now and see if we can understand a little bit more about what's behind the scenes. So, let's see, got to move the Zoom tool again. See, behind GenderMag, we have 3 personas that we've built in, and a persona, for those of you who don't know, is a fictional person. In our case, these are based on tons of data, and they are representatives of certain ranges of users. But in GenderMag, these are only groups of cognitive groups of users, I guess we'll call it. So for GenderMag, all of this is from the perspective of 5 cognitive facets. The user's motivations for sitting in front of the screen, their information processing style, their computer self-efficacy, which is a particular form of self-confidence, their attitude toward risk, and the way they learn new technologies. So these 5 facets. So let's take a look at one of these, Abby. Now, don't try to read all this. All I want you to notice so far is Abby fits on one screen. So if you have experience with personas before and they go on and on for pages and pages, this isn't like this. This is intended for busy software professionals. And it's got bullets and underlines, so it's very easy to navigate. All right, next thing I want you to notice, I've just put this wonderful line in the middle. The top half is entirely customizable. So in the previous example, I dressed Abby as a judge. Abby can have any job title, can live anywhere, can be any age, can have any picture, any hobbies, let's see, I think I said job title before. She can have any of these things. But what you can't change about Abby, any gender, by the way, too. What you can't change about Abby is this. This is her cognitive profile. If you don't like this, pick a different persona. We also have a Tim and a Pat. And all of them have values for these 5 facets. Once again, motivations, computer self-efficacy, attitude toward risk, information processing style, and how they learn new technologies. So let's look at one of these. Facet number 1, risk. Okay, Abby is really busy. She rarely has spare time. And so she is risk averse about using unfamiliar technologies that might need her to spend extra time on them. Now, no, this doesn't mean she's a technophobe. She's perfectly comfortable with technology, but she's risk averse about taking on a new one that she might have to spend a lot of extra time learning. So let's look at some of the data behind Abby. So, and the risk facet. Each one of these facets is backed by at least 5 independent empirical studies, usually done by other people, but sometimes also done by us. This is just data from one study, because I'm not going to try to give you 5 studies. And the blue is men and the yellow is women. This is from a group of 1,000 people. And the only 2 genders that we had in that group were men and women. So first thing to notice, look how much overlap there is between the genders. So here again, this is just another way of saying you can't divide the world up into typical men, typical women, typical anything else. It doesn't work. Second thing to notice is look at the differences in distributions. So when we talk about there being statistical differences among genders, this is what we're talking about, the distributions. All right, so I've mentioned that we have 3 personas. One is Tim, and his mission is to look out for the interests of all of these relatively risk-tolerant people. We also have Abby, who you've met. Her job is to look out for the interests of these people. And Pat's job is to look out for the interests of these people. Now I've added a vertical line here separating Tim from the rest. So suppose, hypothetically, that your XAI system only supports people on the Tim side of the line. How many men from this sample would you be excluding? About half. How many women? About 3/4. This is why we talk about there being statistical differences among the problem-solving styles we're talking about here, statistical only. And it's also why, if you support these problem-solving styles, you're also supporting a wider diversity of gender than you otherwise would. Okay, so let's try to apply this to XAI. So we're going to continue our little example of how GenderMag works. Here is an explanation from Netflix. I took this pretty recently. Actually, this was a recommendation for me. So let's remember again how this GenderMag thing works. So we've got some scenario. Here we've changed the scenario. Abby is on Netflix and is getting ready to pick some movie to watch. And so what we, the developers of this explanation, so we work for Netflix, what we want the user to do is follow these recommendations today and in the future. Otherwise, why would we be giving them? All right, so let's try to walk through this. The way we're going, the question that we're going to try to answer is, if this is what's on Abby's screen, will they do this? Will they take this recommended, action that we want? In other words, follow the recommendations. And if yes, why? We're also going to answer it for Tim. Remember, Abby is risk averse. Tim, on the other hand, is risk tolerant. Okay, if this is what Tim sees, will they do this? Why? All right, so let's try it. So in this situation, 3 out of these 4 recommendations are, shall we say, failed tests. No, Abby is not at all interested in these. These are not attractive except for one of them. So will Abby take the recommendations? Here's what Abby says. Remember, Abby is risk averse. She doesn't want to waste her time looking at a bunch of shows that she doesn't think she's going to like. Abby says, this AI is lame. Ignore it. So Abby is not going to take the action we wished for. And this wonderful recommendation system with its explanation is sending Abby away. Okay. Tim, on the other hand, is risk tolerant. And Tim is pretty happy with this. It's like, okay, I would not have thought of these before. This gives me variety. I'm interested. Okay. So the answers are coming out differently based on someone's attitude toward risk. Okay, risk tolerant, risk averse. That's how we're applying that facet in Gender Mag. And what we've got now is lost market share. Okay, let's look at another one. Information processing style. When people are trying to solve a problem, they usually feel like they need more information, and there are different ways of gathering it. Abby is a comprehensive information processor, so she likes to get her head around something, gather a fair amount of information to get a good understanding of the problem before she goes forward trying to solve it. Tim, on the other hand, is a selective information processor. He likes to take a little information, act on it right away, and if he then discovers that wasn't enough, gather a little more, then act, a little more, then act. So Tim is very iterative. Abby is more bursty in the way she gathers information. Here's an amazing graph that's probably making your head spin. Don't worry, I'm going to read little bits of it to you. But this is some data on 2 people. The top is a man, the bottom is a woman. And this is a sense-making graph. And so all you need to understand about these colors is that these kind of pastels, these are information gathering colors over time. And these brighter colors, these are taking action colors. So this is the man at the top. This is the longest period of time, a little over 5 minutes, that he spent gathering information before doing something with it. About 5 minutes. Mostly the times gathering information before taking action were very, very small. Okay. His longest time is shorter than her shortest time gathering information. She goes gather, 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 gather. Okay, I get it. Gather, 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 gather. I get it, I get it, I get it, I get it. Okay, much more bursty. Both of these are perfectly good styles. Which ones do we support in XAI? Probably only this one. So let's apply this to XAI. So we're back now to the judicial scenario. And here's the judge's assistant. And what Abby's trying to do is understand the prediction and then act upon it, make a decision about how long to sentence this defendant for. The AI says Abby is going to reoffend. And so you ought to throw her in jail. And so here is a Netflix style explanation of that. Abby has juvenile priors. If she hadn't had Ileana has juvenile priors. If that hadn't been true, then I would have predicted that they won't reoffend. Okay, so that is a Netflix style explanation for that. Abby, the comprehensive information processor, is frustrated. She's got hardly any information here. She's also misled, and she's going to throw Ileana in jail. You'll see why she's misled in a moment. Here's Tim. He's happy. He's a selective information processor. Okay, I get it. I'm going to throw her in jail. So in both cases, Ileana's going to jail. Now here is a better style, more complete and actionable. This is one that came out of a paper John Dodge wrote in 2019 with some colleagues at IBM. So a longer explanation, Ileana's race is African American. If her race had been Caucasian, she would have been predicted as not likely to reoffend. Oh, that's interesting. Her age is 18 to 29. If her age had been older, she would have been predicted as not likely to reoffend. Ileana has juvenile priors. That's the thing that we had before. If it had been no, they would have been predicted as not likely to reoffend. And here's what Abby really wants. Changing other attributes will not change the prediction for Ileana. Okay, so now what Abby's got is fairly complete information. She can see exactly what the sensitive factors are and that the other ones aren't affecting the decision. So Abby is no longer frustrated. Her comprehensive itch has been scratched, and she's also no longer misled. And because Abby has seen that these reasons are factoring in way more than she should, she decides not to send Ileana to jail. Tim is still happy, but he's not misled anymore. And he too chooses not to send Ileana to jail. Why is Tim happy, even though there's all this extra information? Because it's still set up in a way that a selective information processor can make good use of as much as they want. It's in bullets. It's got boldface. He can stop at any point. He doesn't have some wall of text facing him. So a design like this satisfies the comprehensive information processor and the selective information processor. That's what you want. Okay, we want to take down bugs that get in the way of one or the other of these. We don't want to divide. Okay, so how has this panned out in real world products? Here's some data from 17 teams. This is based on how many features they evaluated using this method. The lowest percent, these are real world teams looking at their own real world products. The lowest percent is 12%. What does that mean? 12% of the features they looked at using GenderMag, they found inclusivity bugs. Look at this one, 100%. Every single feature they looked at, they found something. Now, actually, that team is better off than this team. Why? Because that team evaluated early while things were still in the lo-fi prototype stage, just sketches. And so when they saw that, they said, okay, back to the drawing board, and they didn't waste a dime implementing that system.
5 minutes, Margaret.
Thank you. This is perfect. What do you do when you find things like this? Well, it turns out that when you find something like, hey, this is never going to work for a comprehensive information processor, that tells you what to fix. How could we make it work for a comprehensive information processor? We need to enable them to get more information. So the fixes just fall in your lap. Here's some data from a little case study that Microsoft did. Actually, this relates to the paper yesterday on explainable smart search. So this was a smart search, and they enabled us, they allowed us to publish this, by the way, and even name the product. So that's pretty cool. Anyway, before they ran GenderMag, that product had been out there. And so they took the old product and they ran an empirical study, and women failed the task more than twice as often as men. Actually, there were 5 tasks that corresponded to their main use cases. So the women failure rate was over twice as high as men. And by the way, here again, we had only 2 genders in our data. After they made the changes that GenderMag suggested to their design minds what to do, the failure rate got better for everyone, and the gender gap completely disappeared. That's what you want. So here's a call to action. Society has problems that only we can fix, and this is one of them. So how can we go about this? Explaining AI fairly is what we want to do. So we need to base our work on theory and foundations from social sciences. one way to, and we've been getting lots of contributions on how to do that at this workshop, and there's more in the literature. So one way you can do it is you can read about them and their implications. You can use guidelines derived from them, which are published and out there. Also, we need to make explanations actionable, and that's something we've been talking about at this workshop. We need to empower users. These decisions affect their lives. And we need to understand that diversity exists and that we need to support it. So give the user control to switch from one explanation to another as the situation changes. And use GenderMag or use GenderMag when you are evaluating and designing your own explainable AI systems. And of course, evaluate with humans. So that's it. I am open for questions. And I guess somebody's going to need to keep an eye on the chat.
Yeah, I'm monitoring the chat. So everyone, you can chat in the Zoom chat as well as in the Rocket chat. I'm monitoring both.
Or maybe just, yes, go ahead.
Are you done?
Yes.
Thank you very much. Thank you, really, really. It was fascinating, and I know there's people interested in asking questions. I have one question that is very specific on one point there that I would like to go first while people warm up to questions. When you define the information processing and risk takers, it seemed to me that even I understood them as two different facets. But it seems to me that the risk taker is always going to be the same type of information processing. That's that's what I want to ask. That was my perception, that the person who is risk adverse is always going to be more careful and try to get more information before making a decision. Is it not?
So Rosina, that's really an awesome question. And it kind of has two questions in it. So first, I'm going to answer one piece of the question. The definitions of these facets are orthogonal, but any one can influence another one. So it is true that risk can influence the amount of information that we want to gather, but they won't always go hand in hand. And so this little graphic that I've shown you a couple of times in this talk is actually real data from one of our empirical studies. And so over here on this side of the graph, this is the number of people in that study that were pure Abbeys. All 5 of their facets lined up with the Abbey facets. So for your example, that means they were both risk averse and comprehensive information processors. Over here on this side of the graph, these are the people that are pure TIMs. Okay, and so what that means is they were risk tolerant, they were selective information processors, and the other facets. And so what you can see is a tiny little proportion of the people in this graph were pure Abbeys. And also a tiny little proportion of the people in this graph were pure TIMs. And everybody else was a mix. 4 Abbey facets, 1 TIM facet, 3 Abbey facets, 2 TIM facets, and vice versa. Another thing to notice is that the women skewed toward the Abbey side of the graph and the men skewed toward the TIM side of the graph. That just comes back to those statistical differences in distributions, which is why the supporting multiple problem-solving facets also, as almost a side effect, supports multiple genders.
Outstanding. Thank you very much. David, you have a question?
So thanks for a great talk, Margaret. There's so much that I learned. My question is one more on the challenge for one individual to, in some sense, be a master of both AI and social sciences in order to be able to bring to bear social science expertise on their designs and implementations. So it's not clear to me that one person can do that. This needs to always be a team, but there will be situations in which that won't be affordable by, say, the organizations trying to develop these. I'm wondering, do you see implications or what have been the shifts, if any, or what should be the shifts in any, in terms of educating people to be able to do these kinds of things?
Thank you for that question, David. I love it because that's one of the problems that GenderMag is aiming to solve. And so what I've done in this talk is taught you all how to use it. And so all you need, let's see, I'm probably not going to be able to easily get back to that slide, but all you need is the GenderMag kit, which is all freely downloadable, which has the Abby persona. So you just take the Abby persona or the Tim persona or the Pat persona, whichever one you want to support, to add support for right now, and walk through your own AI system and ask, just according to those facets, is Abby going to like this or not? So we did this twice already. Actually, let's just get back to one of these examples. Sorry if I'm making you dizzy. Yeah, this one right here. So we walked through it. And you all understood it, even if you have no social science background. And so this is a way to distill all that social science and give it to professional software developers and AI people and people without the social science background, and still be able to harness that in a way that makes a difference. So what we've found, GenderMag's been out there now for about 4 or 5 years, and we've found that it doesn't require any background in social science to make good use of this. Right now, we're doing a lot of field work with the Oregon State University IT professionals, and they're using GenderMag, and I don't think they have hardly any HCI people on their teams. HCI people are better at it, and people with social science backgrounds. They can get more out of it, but everyone can make their systems better. So yes, interdisciplinary teams, but no, without somebody that has that background, you don't get off the hook. You can do this stuff easily.
I see. Thank you.
Mhm.
So we have a 5 minutes break now at 11 Eastern. That's my time. We'll start the next session. So we have a question from Mark. We'll continue with the questions for another few minutes, so we do not interfere with the time. But if anyone wants to take a break, we'll have a couple more questions. Mark?
So really nice talk, Margaret. I very much enjoyed it. And I was just wondering, I mean, obviously you put a huge amount of work into characterizing these stereotypes and being able to sort of stand over them. Do you think there's any room in the future for being able to, in a sense, try and induce these or learn these in some automated way, rather than having to handcraft them, as it were?
That's an excellent question, Mark. Actually, that raises two answers I want to give you. The first was stereotypes. What some people worry about when they are first introduced to GenderMag is that maybe it's going to introduce stereotyping behavior among the people who are using it. And so we wanted to know that too. And so we collaborated with a stereotyping expert to find out. And the bottom line is, using GenderMag, people stereotype less than they do naturally. So there are standards out there. And so we have a paper about that with all of the results. And that was in CHI 2017. And I'm very proud of that paper and very happy that we were able to bring that expertise in that area to find out this question. Let's see, there was a second piece to that question. Oh, and it was about whether or not we can learn these personas. Some people are right now working on automatically generated personas, not for this purpose though. And so it definitely is a possibility, but I don't think that it's a possibility for this kind of persona, because this kind of persona is trying to be all about supporting diversity. So we're not aiming for the people, the majority. We're aiming for the whole spread. And not only that, all 5 of our facets are theory-based. So one of them, the risk aversion facet, I mean, there's a ton of social science literature about risk and how it pans out and whether it varies by gender. And so I have a feeling that although I have a feeling that these facets have to be very deeply understood to be able to make a real difference to the diversity dimension you're trying to make a real difference to. By the way, coming soon, we have Socioeconomic Mag, which has its own facets that we've spent like 2 years digging around in the social science literature to try to find the right set. So, so I don't think you can get away from that bit.
Thank you, Margaret. I would like now to invite the next session authors and chair to take over. We still had a very good question here, but I'm afraid we're running out of time. I encourage Margaret to see the question in the chat. And thank you very, very much for your talk. It was a pleasure to have you. Sylvia?
Thank you, Margaret. It was really a good talk. I hope to make your question on the chat. We will also ask Turgin to ask the question in the other chat. So Tobias, are you here? Could you please share your screen? Okay, great. So we will now start the session of presentations, like oral presentation. And
yeah.
Yes, we have now Tobias Uber. You can start if you want.
Okay, so hi. Just a laser pointer. Yes. Okay. Hi, my name is Toby, and I will present our paper benchmarking perturbation-based saliency maps for explaining deep reinforcement learning agents, which we did with my colleague Benedikt Limmer and my supervisor Elisabeth André. And yeah, it's a very short information motivation. Machine learning algorithms like deep reinforcement learning are increasingly opaque due to a huge number of parameters and an incomprehensible structure. And to explain these black boxes, saliency maps try to highlight parts of the input that are important for the decision of the network. So we do not only show, okay, take the move right action, but we also show, okay, this was important. However, in recent years, there was a plethora of different saliency map methods that was proposed. So now we have the problem, which saliency maps do we even choose? And one criteria for this is the requirements that the methods have. So there are model-specific saliency methods, for example, gradient-based models, methods which need you to have access to the model's gradient, or modified propagation algorithms that need you to know the specific architecture of your model. But if you do not have the architecture of your model because for some reason you just don't have access to it because it was trained by some other company or something like this, then you need model-agnostic methods like perturbation-based methods. And another selection criteria for your saliency maps is evaluation metrics. And one, and I think the most important one, is human user studies, which we heard a lot about just now. And I think the main goal here is to find out how useful the saliency maps are for end users. And a problem is that designing suitable user studies and acquiring participants is very time consuming, as we also just heard now. And another category of evaluation metrics are computational measurements. So here the main goal is more to see how faithful is our saliency map to the reasoning of the model that we want to explain. So we want to make sure that the areas that we highlight actually were the most important for the model. Once this is implemented, it's very cheap to compute for different algorithms. And while it does not measure if the information is actually useful for the end users, we can definitely use it to pre-select methods which we can then evaluate in user studies. And those computational measurements is what we did. Okay, what did we use specifically? As a test environment, we used the arcade learning environment, which is probably the most common benchmark for reinforcement learning algorithms with pure visual input. And we used Frostbite, Breakout, Mrs. Pac-Man, and Space Invaders as examples. And the agents were just classical DQN agents, where we have the raw pixel values, feed them through 3 convolutional networks, then 2 fully connected convolutional layers, then 2 fully connected layers, and we get Q values for each state action pair. And all our saliency maps were perturbation-based saliency maps. What we mean by that is that they work in 2 steps. At first, the input image is perturbed, for example, by occluding one square with black color. And then those perturbed images are fed into the black box model, and we measure how much this changes the prediction of our model. So for example, if we assume the original confidence was 0.9 and the new confidence is 0.87, this was not an important area of the input. And for example, here, if the black square is occluding the ghost in the middle of the screen, which can eat Pac-Man, then the confidence in the action changes a lot. And this seems to be very important. So we can highlight this in a saliency map, and then we can interpolate this to be the same size as the original input image and overlay this in a heat map to show to a user. Okay, this is basically the first algorithm that we use, the occlusion sensitivity, how we call it. It's just using gray patches normally over the image and then taking the difference to the original confidence. Or in our case, we use the implementation by TensorFlow's TF-explain. Here it is 1 minus the new confidence, which is equivalent to the original confidence minus the new confidence. It's just shifted by a constant value. Another perturbation-based approach we used is noise sensitivity, proposed by Gredanos et al., especially for Atari agents. And here they try to avoid choosing a color for occlusion by using Gaussian blur in a circle around every nth pixel. And then they measure the change in prediction again, but here they take the difference in all the output logic values. So they take all the actions into account and do not only look at the action that the agent chooses. RISE, randomized input sampling for explanation, is perturbing the input by generating random masks and then multiplying them with the input. And those masks have values between 0 and 1, so it looks like fading out black patches in here. And then they calculate importance, and the important part here is that they take the probability of the probability with which each pixel is occluded and the actual value of each pixel into account in the calculation. And the last algorithm you looked at was LIME. It's probably the most famous perturbation-based algorithm. Here, the perturbation is done by first finding superpixels in the input picture with segmentation algorithms like the quick-shift algorithm we used because it's the default algorithm. And then it blackens out those superpixels and feeds this into a locally weighted interpretable model, which is trained to approximate the original model. And then by analyzing the weights of this interpretable model, we get relevance values for each superpixel. Okay, after we implemented all those methods, we saw that occlusion sensitivity with gray patches and noise sensitivity had very strange saliency maps at first. This is also an observation that Gredanos et al. Made in their original paper, because they said that the Pac-Man agents were just really bad. The DeepQN agents are bad at playing Pac-Man, so they said, okay, the agent is just looking around everywhere in the screen. We looked into how this occlusion worked here. And for the Pac-Man agents, as you've seen before, this noise appears to be grayish. And the gray occlusion is, of course, gray. And this is a color that has a lot of meaning in the Pac-Man environment. So we think that the perturbation or the occlusion did not have a big enough effect on the original screen. So to make it more similar to the other two approaches, which worked reasonably well, we used black patches here. And for noise sensitivity, we also tried to just use a black circle and forget the noise altogether. so that noise sensitivity and occlusion sensitivity only really differ in the way how they compute the importance per pixel, where noise sensitivity takes all the actions into account and not only one. And then we looked at some pictures at first. We did not cherry pick those pictures, but choose them with the highlights algorithm proposed by Ofra Emir yesterday. And the main takeaway is that for Rise, occlusion sensitivity with black, lime, and noise sensitivity with the black circle, we can see that all of them focus on the agent, which is probably also the most important thing of the input. And noise sensitivity and occlusion sensitivity with gray, you can see that it's just looking around. But looking at images can be very misleading. So of course we did actual measurements. What did we measure? For one, we did sanity checks as proposed by Adebayo. So we took the layers and we cascadingly randomized the layers of our network and generated saliency maps for those models with randomized layers. So this is shown here, and you can see for Rise, for example, even after randomizing the last fully connected layer, the saliency map is completely different. And for noise sensitivity, you can already see in this example that the first fully connected layer, so the last actually, did not have that much of an impact. Also here, we measured the difference to the original image with Spearman correlation, structural similarity index, and Pearson correlation of the histogram of gradients for 1000 steps of the Pacman environment. And the results show that occlusion sensitivity on Rise had a very high dependence on the parameters. So the images, the saliency maps were very different to random saliency maps. And noise sensitivity, black and blur and lime, they showed quite a lot of independence on the last fully connected layer, which we think might have happened because they take all the actions into account, and just changing all the logic values might not relate to really changing the action of the decision of the agent. In general, compared to the gradient-based saliency maps that Adebayo et al. Tested, the sanity checks for our perturbation-based agents were much better, where you can see, for example, Pearson, which is the hawk here, for gradients seldom went under 0.4, and for ours it seldom went above 0.2. So I think in general, the perturbation-based saliency maps are very good at this kind of test. Additionally, we tried input degradation tests or ablation tests. Here, normally the input is gradually deleted from the input, and starting with the most important pixels, and then you would expect that the agent's confidence would fall quickly. However, this doesn't make a lot of sense because this is also how our saliency maps were created in the first place. So we used an insertion metric, which has been proposed in some newer papers. Here you start with a black or an empty input image and then insert the most important pixels cascadingly, gradually, and you expect the confidence of the agent to rise quickly. And here we measured again 1000 steps for all four of our test environments. And for Pacman and Space Invaders, you can see that occlusion sensitivity seems to perform the best, followed by Rise, and then the others are a little bit indistinguishable, and occlusion sensitivity with gray definitely was the worst. Interestingly enough, the noise sensitivity with blur, which was just proposed for Atari agents, was the second worst approach here. And we have very similar results for Breakout and Frostbite, where occlusion sensitivity again was the best, Rise the second best, and the others were very similar to each other. Okay. We also calculated the mean runtime and saw that, okay, just changing the color is faster than applying blur or finding superpixels and these masks. So occlusion sensitivity was also much faster than the others, followed by noise sensitivity. So in conclusion, we found that occlusion sensitivity with black color seemed to be the best suited for our Atari agents, followed by Rise. A little more general conclusion is that hyperparameters are very important for those kinds of saliency maps. So only changing the color from black to gray had a huge effect on those occlusion sensitivity maps. And there were also a lot of other parameters which we tried to optimize for all our approaches. And yeah, very surprising to us, and especially to me, was that noise sensitivity performed the worst in our tests. If we exclude the occlusion sensitivity with gray, which you can just change the color of. And a little bit more better observation was that all perturbation-based saliency maps performed well in the sanity checks. Only Lyme and noise sensitivity were less dependent on the parameters of the output layer, which I think is very interesting and we should look into more. And in future work, we want to do more user studies to build up on this. And that's it.
Okay.
Yeah, the implementation is here. Yeah, sorry.
No, great. You are perfectly on time. And now we have a couple of minutes for questions. And thanks again for your presentation. Rosina, do you want to ask a question?
Thank you, Sylvia. Thank you, Tobias, for this work. I have two questions for you, actually. One is, I did not really understand how you did the assessment of faithfulness. And the others, I believe you were with us yesterday, and I wanted to see how the work on the baselines that we saw yesterday relates to this, and how could that help, or your work could help that? Okay,
the first question is basically both our methods were aimed to look at the faithfulness. So the sanity checks are like the first test. If you're not dependent on the neural network's parameters that it learned, you're definitely not faithful to the model. So if you fail the sanity checks, you're definitely not faithful to the model. And this input degradation also tries, like, it's all just approximations. There's a lot of work to be done to get better evaluation metrics. This is just the best we had. Is trying to, okay, if we find the most important features with the saliency map, then removing this feature should make it degrade fast, and adding this feature, like if this is the most important area, just this image should already work very good for our agent. So this is why I called it faithfulness.
Okay.
And for the second question, like, I really enjoyed this talk yesterday, and it relates very much. It's just, I did it for visuals and for like saliency maps that do this just by perturbation. And he did it for example, integrated gradients, which is some kind of a mixture between this perturbation and the gradient-based approach. So it relates very, very much. And yeah, this is basically the answer. It very much relates. And yeah, I don't know, do you have follow-up questions to this maybe?
Thank you again, Tobias. I think like follow-up question needs to be in our other chat. Please, I will share with you again the link to Rocket Chat. And meanwhile, can you please, Roxanne and Turgina, share your screen?
Yeah, no problem. So let me find the presentation. Yep.
Thank you. You can start if you want.
Well, good afternoon, everybody. It's a pleasure to be in this group. Today, Roxanne Zhang, myself, and also co-lead of the paper, Umang, but also on the line here, would like to take you in the next 15 minutes on the discovery that we found within effects of uncertainty on the quality of feature importance estimates. This work has been very much a team effort between Quantum Black and Partnership on AI with our collaborators from University of Cambridge and Alan Turing Institute. Just to give a little bit of understanding, the Quantum Black, we are data scientists that work as an advanced analytics consultancy. So we have exposure to different organizations, businesses that are working in analytics and trying to analyze their data in the best possible way. And Partnership on AI is really what it is. It's a partnership among industry and academic researchers that are working to solve real-world problems related to machine learning. So really, we're marrying in this research the academic research with practical industrial need. Now, for the way we would like to structure the next few minutes is to highlight the motivation behind the study with the theoretical underpinnings And then I'll hand over to Roxanne to discuss the experimental setup and share with you some of the empirical findings. And then we'll conclude with what those what implications those have for the real world applications of explainability. So there are two large motivating factors behind this work. One are the vulnerabilities in post-hoc explainability methods themselves that have been raised in the machine learning community over the past few years, which are the properties of the methods themselves. The second problem is the vulnerabilities in the way those methods are used in and applied in real-world applications. So in fact, if we go a little bit more deep dive on that, we've noticed roughly in the last 5 years, since perhaps emergence of LIME followed by a beautiful package where the authors of SHAP produced together with their papers, we've really seen a welcome surge and interest in adoption of explainability methods in industry, whether it's manufacturing, financial services, or healthcare. It's increasingly viewed, including regulators, as a key for trust and downstream adoption. But we've also noticed some red flags indicating over-reliance. Specifically, and this is perhaps deeply rooted in the fact that majority or large number of real-world applications still face issues of model under-specification, resulting into a whole range of models with comparable accuracies and comparable performance that differ slightly in the initial states or the inclusion of particular features. That leads to data scientists along the track where they are relying on post-hoc explainability to inform model selection. And this perhaps talks a little bit to Margaret's earlier discussion, when depending on data scientists' own risk averseness or the level of how they problem think, they may discard all the models that their understanding of the features do not corroborate with the explainability drivers. And as you can all appreciate, this leads to a significant confirmation bias alongside vulnerability to manipulation. So what we really wanted to focus in this work was deviating away from assumption that it's just the explainability method itself that is vulnerable and can vary, which has been thoroughly investigated by the team of Dylan Slack in 2020, but actually appreciate that the assumption that the model is fixed is restrictive. In fact, we know for a fact that existing methods for generating explanations tend to explain a point estimate, which are assuming that there's only a single model exists. And without really trying to marry the frequentist and Bayesian approaches here, we're just going to think of it as from a data scientist perspective, that when we are trying to appreciate the uncertainty within the model estimates for explainability, we can subsample from the posterior, and meaning that we fix the same model class with the same model specification, parameters, and features, but the models themselves may vary in the training samples and the initial states. Now, the title of this paper was something about uncertainty, something about the quality. So I wanted to just clear this out for the rest few minutes, how defining uncertainty is a variance in the predicted probabilities over the set of candidate models. And the way we're defining quality is, in addition with variance in explainability, we're looking to metrics that Tobias have mentioned, but largely they all stem from Shapley value axioms. This is faithfulness, how consistent are the feature attributions with some ground truth. Typically, it is generated via occlusion. Monotonicity, so do we expect that important features increase the model performance in the order of their importance? Complexity, how succinct are explanations, which is a very important factor for practical applications and usability of explainability techniques, and efficiency. does the explanation capture the predicted value in full, or are there some residual values? So with this in mind, I would like to hand over to Roxanne to highlight the experimental setup.
So I'll be talking about experiment setup. So given the very empirical nature of our work, so we run extensive experiments that's over 168 hours on a 24-core Xeon machine. So we consider a broad range of explainers coupled by tabular and image data, so mainly tabular, with like multiple commonly used machine learning model class. So for example, like for tabular data sets, the experiments described in this work involves a selection of gradient boosted trees, multi-layer perceptrons trained with publicly available tabular data sets, for example, like adult, breast cancer, compass, and diabetes. And then we subsequently running 5 types of explainers, including exact, tree, and kernel SHAP, also the integrated gradients and smooth grad. So for each model dataset pair, we sample from posterior across initial states with a uniform prior. So between each iteration, only the model initialization and the training subsets are permuted, while other things, for example, like model architecture, training procedure, and evaluation parameters remain fixed. So the resulting point estimates makes up the distribution of a model's predicted probabilities, where the expected values defined the model confidence, and also the variance defines the epistemic uncertainty. So in simpler words, first we calculate uncertainty estimates for feature importance by subsampling from training sets to find the good candidate models. And then we try to explore how explanations of an ensemble are related to explanations of each model within the ensemble. And then we are trying to find out if the feature importance explanations for out of distribution data points are unreliable under various evaluation criteria. So moving on. So we empirically observe that. So for variance in underlying model propagates to the variance in explanations, and formally prove for Shapley values that the variance of explanations of an ensemble model is equivalent to the mean variance in Shapley values of the learners. So as you can see and above in the, there's like a 12-dimensional out of distribution sample on the left, where a point on which the ensemble of the models were most uncertain. It is also associated with like larger and wider spread of explanations attributed to each of the 12 features. And in contrast, as you can see on the right-hand side, so that's an in-distribution example. So a point on which the ensemble of the models had agreement, this will yield lower uncertainty in the explanations. And these observation is also holds for different model classes, for example, like different explainers and different data sets that we all consider in our model. And also the most interesting finding is not only about the larger and wider spread of the Shapley values for each features, but also the sign change of some features. So depending on the model, it can be like both positive and negative drivers. So moving on. So another finding we had is, as you can see here, the low model confidence was associated with degradation in quality of explanations. So in particular, complexity of explanations decreased for the samples on which the model confidence is high. And also here we define model confidence as the mean of the highest predicted probability across all classes. And we also try to find the explanation quality suffers for the models with low model confidence. And again, those findings holds for different model classes, different explainers, and different data sets that we considered. And next one. So following up on the previous findings, so contrasting the quality of explanations between out of distribution and in distribution samples, we observe like a drastic difference, decrease in quality across range of evaluation criteria and also type of explainers. So as you can see here, so the complexity and monotonicity degrades significantly for all explanation methods considered. For example, like for explainers which are not 100% efficient by design, let's say tree SHAP, the efficiency is lower in out of distribution samples. And another, our experiment results also confirms that, for example, like kernel shape approximation are locally accurate and fully meet the efficiency axiom. So for example, the score equals to 1 in both out of distribution and in distribution samples. So talking about faithfulness. So with respect to faithfulness, the differences between out of distribution and in distribution samples are less pronounced, but still holds for exact shape, tree shape, and smooth grad. So I'll hand it back to Torgen talking about the implication.
The few implications that we wanted to highlight in the remaining minute is that we recommend that data scientists and data practitioners, when interpreting feature importance scores, consider not just point estimates, but the entire distributions. Then we would move on to the recommendation that for samples that are uncertain, that the model is uncertain, feature attribution techniques should not be used. And here we really urge considering alternative classes of explanations, such as uncertainty attributions, as presented by Clue paper. And finally, we believe that what we need as an industry, as a community, is frameworks and standards for routine explanations, standardization in terms of viewing the quality of explanations so that they can be used routinely. We're running out of time, so I'll take any questions on the Rocket chat. Thank you for your time.
Thank you to Jean, and thank you, Roxanne, for the presentation. Do you have any question? We have 1 minute, and if you want, the next presenter can start sharing the slides. We will stop recording. Ohana.